Hook. In 1981, a hotel walkway collapsed in Kansas City. 114 people died in 90 seconds. The cause? One tiny change to a bolt connection. One change. That's it. Engineers had approved a design that nobody actually stress tested under real load. And the result was the deadliest structural failure in US history at the time. But here's the wild part. That disaster didn't just cause grief. It rewrote the entire rulebook for how we build things today. Promise. Stay with me for the next 10 minutes. Because you're about to learn how 5 catastrophic engineering failures, bridges that twisted themselves apart, buildings that liquefied the ground beneath them, and a dam that drowned an entire valley permanently changed the way every structure on Earth gets built. These aren't just horror stories. They're the reason your office building, your highway overpass, and your apartment complex don't kill you every single day. Let's go. Section 1. The Hyatt Regency Walkway Collapse. Kansas City, Missouri. July 17, 1981. A tea dance was happening in the atrium. About 1,600 people packed into that hotel. 3 suspended walkways hung overhead like floating bridges. They were beautiful. They were also a death trap. The original design called for one continuous rod to support the walkways. But during construction, someone made a simple change. They split that single rod into 2 separate rods to make assembly easier. Sounds harmless, right? Wrong. That change doubled the load on a single nut and washer connection. Instead of holding the weight of one walkway, that connection now had to hold 2. Nobody caught it. The calculations were never rechecked after the modification. At 7:05 p.m., the connections failed. The 4th floor walkway dropped onto the 2nd floor walkway. Both crashed into the crowd below. 114 dead. 216 injured. The investigation revealed the connection was only designed to handle 60% of the required load even before the modification. After? It was carrying twice what it should have ever seen. What changed forever? Engineering review processes. After Kansas City, the entire industry overhauled how design changes get approved mid-construction. Today, any modification to structural connections requires a full reanalysis and sign-off by a licensed engineer. Every single time. No exceptions. The Kansas City collapse didn't just kill 114 people. It created the modern change order review system that has quietly saved thousands of lives since. Section 2. The Tacoma Narrows Bridge. Washington State. 1940, this one is almost poetic in how it failed. Engineers built a suspension bridge spanning 2,800 feet across Puget Sound. It was elegant. Slim. Aerodynamically clean. And that was exactly the problem. On November 7, 1940, wind speeds of just 42 miles per hour hit the bridge. Not a violent storm. Just a steady, moderate wind. The bridge started twisting. Slowly at first. Then violently. For 4 hours, the deck oscillated and writhed like a ribbon in a fan. A local newspaper reporter named Leonard Coatsworth had to abandon his car mid-bridge. His daughter's dog was still inside. The car and the dog went down with the bridge when it finally tore itself apart and fell 195 feet into the water below. Engineers had completely ignored the aerodynamic forces on the structure. They designed for weight loads. They designed for tension. They never designed for resonance. The wind hit a frequency that matched the bridge's natural vibration frequency. And it shook itself to pieces. Here's the cliffhanger. This exact same phenomenon, resonance failure, had actually been documented in bridges before Tacoma Narrows. Engineers knew it could happen. So why did they build it anyway? The answer involves a famous engineer, a cost-cutting decision, and a controversy that still hasn't fully been resolved 80 years later. Wild fact break. Before we get to that answer, stop and think about this. There are currently 617,000 bridges in the United States alone. About 42,000 of them are rated structurally deficient right now. That means roughly 1 in every 15 bridges you drive across has known structural problems. The fixes needed would cost an estimated $125 billion. That money hasn't been allocated. Just let that land for a second. Okay. Back to the resonance problem and how engineers fixed it. Section 3. After Tacoma Narrows, bridge engineering completely changed direction. Engineers added wind tunnel testing to every major bridge design process. They widened decks. They added aerodynamic stiffening. They created open truss designs to let wind pass through rather than push against the structure. The Golden Gate Bridge, which opened 3 years before Tacoma Narrows, was quietly retrofitted with stiffening trusses underneath its deck. Engineers tested scale models of every proposed bridge and wind tunnels before a single piece of steel got ordered. But resonance wasn't done humiliating engineers. In 2000, the Millennium Bridge in London opened to the public. Within 2 days, it had to close. Not because of wind. Because of people walking. About 90,000 pedestrians crossed in the first 2 days. The slight sway of the bridge caused people to unconsciously sync their footsteps with the bridge's movement. That synchronized walking amplified the sway. The sway made more people sync up. A feedback loop of human feet literally made a brand new bridge wobble dangerously. Engineers call it synchronous lateral excitation. Regular people call it terrifying. The fix cost $8 million. Dampers were installed beneath the deck. The bridge is now one of the most vibration-stable pedestrian structures ever built. Lesson? Forces you can't see, resonance, harmonics, crowd dynamics, are just as deadly as the ones you can calculate on a blueprint. Section 4. The Johnstown Flood. Pennsylvania. May 31, 1889. A poorly maintained dam owned by a private hunting and fishing club failed after heavy rainfall. The South Fork Dam had been modified over the years. Its spillway was narrowed to allow carriages to cross. Screens were added that clogged with debris. The dam's height was actually lowered to build a road over it. Every change made it weaker. When it finally failed, it released 20 million tons of water in 45 minutes. A wall of water 40 feet high and half a mile wide traveling at 40 miles per hour hit Johnstown. It carried houses, trees, train cars, and bodies. 2,209 people died. Entire families were wiped out completely. The human story here is devastating. Survivors described hearing a sound like thunder before the wave hit. Some had maybe 10 minutes of warning. Most had none. Children were found miles downstream, still in their beds. Here's what changed. The Johnstown flood triggered the first serious legal movement around dam safety in American history. It took decades, but by the 1970s, every state had formal dam safety programs. Federal oversight of high-hazard dams became mandatory. Today there are roughly 91,000 dams in the United States. About 15,600 are classified as high-hazard, meaning failure would likely kill people. Because of Johnstown, each of those dams gets inspected on a regular cycle. Without that disaster, that regulatory framework likely doesn't exist. Section 5. The Ronan Point Collapse. London. 1968, a 22-story apartment tower. One gas explosion on the 18th floor. The explosion blew out a load-bearing wall panel. And then something nobody expected happened. The floor above the explosion lost its support and collapsed. That falling floor hit the floor below. Domino effect. An entire corner of the building peeled away from the 18th floor to the ground. 4 people died. But that number obscures the actual horror of what engineers discovered afterward. The entire building, and hundreds like it across Britain, were held together with almost no structural redundancy. Remove one panel and the whole corner falls. This design method was called large panel system construction. It had been used to rapidly build affordable housing across Europe. Millions of people were living in structurally vulnerable buildings. After Ronan Point, engineers introduced the concept of progressive collapse resistance into building codes. The idea is simple. If one part fails, the rest of the structure shouldn't come down with it. Today this principle is built into every major building code on Earth. It's why the World Trade Center towers didn't collapse the moment the planes hit. The structural redundancy allowed the buildings to stand long enough for tens of thousands of people to evacuate. Progressive collapse resistance is one of the most important invisible safety features in every modern building. And a gas explosion in a London flat in 1968 is the reason it exists. Conclusion. Here's what you just learned. 1 misread bolt connection in Kansas City rewrote how engineers review changes mid-construction. A 42 miles per hour wind in Washington state proved that invisible forces like resonance can destroy structures that look perfectly solid. And a gas explosion in London revealed that millions of people were living in buildings that could collapse like a house of cards from a single failure. These disasters were tragedies. Real people died. Families were destroyed. But the engineering rules that were written in response to each one have saved an uncountable number of lives in the decades since. Every code update, every inspection requirement, every wind tunnel test, there's a human story behind it. That's the thing about engineering failures. They're never just about the steel or the concrete or the math. They're about what happens when we stop asking the hard questions. The moment we think we've got it figured out is exactly when something reminds us we don't. If this blew your mind even a little bit, subscribe right now. Because we've got videos on engineering marvels, near disasters, and the insane science behind structures you walk past every single day. Hit the bell. You don't want to miss what's coming next.